Having finished Chapter 1 now, we understand several properties of vector spaces. And now we're going to talk in Chapter 2 about mappings or functions from one vector space to another. Now, we know that our vector spaces by themselves are abelian groups under the operation of addition. So if it weren't for the scalar multiplication, I would just say that these mappings are homomorphisms. They're going to preserve the operation in V, but they also have to preserve scalar multiplication, so we call these linear transformations. Let V and W be vector spaces over F. A linear transformation from V to W is a mapping. T maps V to W, satisfying, well, part A is simply it preserves the operation in the group. And B, it preserves scalar multiplication. So T of Cx, where C is an element of the field, is C times T of x. So you can prove those separately, or you can use this test for linearity if you want. It really doesn't make any difference. A and B extend, of course, to longer sums. The linear transformation applied to a linear combination of vectors is equal to a linear combination of the T of VI's. And notice the coefficients in the linear combination are exactly the same. So here's a couple of quick problems to just make sure that you know what you need to do to prove that a mapping is a linear transformation. The first mapping is T, mapping the vector space of polynomials of degree less than or equal to 2 to the vector space of polynomials with degree less than or equal to 3. And T is defined to map a function to x times that function plus its derivative. So part A, we want to show that T of f plus g is T of f plus T of g. So I put T of f of x plus g of x, and then I write out what it is according to this definition of T. It's x times the function f of x plus g of x plus the derivative of f of x plus g of x. And just expand that out and use the fact that the derivative of the sum is the sum of the derivatives, and you expand it out maybe one or two steps, you get to this, and that is T of f of x plus T of g of x. Then for part B, I decided to do that separately. T of c times the function f of x. Again, use the definition. It's x times the function plus the derivative of that function. And you know that the derivative of a constant times a function is the constant times the derivative of the function. So again, with maybe just one additional step, factoring out the c, we get to c times T of f of x. So T is a linear transformation. In the second example, we have a mapping from R2 to R2, and we map an ordered pair in R2 to another ordered pair with the absolute value of the first coordinate, comma, the second coordinate remains the same. This one will not be linear. You could start out trying to show it is, and soon you'll see it's not. And it is because I'll put that in a different color, the absolute value of A1 plus B1 is not equal to the absolute value of A1 plus the absolute value of B1. And you get to a point in trying to do what I did up here in part A where you need that, but it's not true. So instead of using a method like I did in number 1, I'm just going to think of an example. Let's take t of, and let's take the ordered pair 1, 2 plus the ordered pair -1, 3. Okay, if we add those two together, we get t of 0, 5. The absolute value of 0 is 0, and so that is 0, 5. But if we do t of 1, 2 plus t of -1, 3, we get the point 1, 2 plus the absolute value of -1 is 1, 3, and our answer would be 2, 5. So we see that these are not equal. If you want to show that a mapping is not linear, the best way to do it is just to show one example rather than trying to prove it in general. These definitions you're already familiar with. If V and W are vector spaces, we have the identity transformation, and we denote it by I sub V, the mapping I sub V that takes a vector space to itself, by mapping each vector to itself. The zero transformation we're going to denote by T sub 0. It means that every vector in V will be mapped to the 0 vector in W. So the range of T0 is simply the trivial subspace of W, which is the set containing the 0 vector. If T maps V to W is linear, then the null space of T is, well, it's the kernel. We already know about this. We can view V and W as groups under addition, and you know that the kernel of a mapping is the set of all vectors in V that map to the 0 vector in W. And so we call that the null space in linear algebra, because we have to consider the scalar multiplication, not just the group definition. And the range of T, well, it's exactly, we called it the image of G under the mapping, the homomorphism, phi. Well, this is the image of V under the linear transformation T. It's denoted R of T, and it's simply the set of T of X where X is in V. You know that it is a subset of W. In fact, it's going to be a subspace. The range of T is also called the image of V under the transformation T. So theorem 2.1 tells us that the null space is a subspace of V and the range is a subspace of W, if, of course, T is a linear transformation from V to W. Okay, so we know already that we have subgroups. So all we have to deal with is really the scalar multiplication. We've done this in group theory. So let's let C be an element of the field, and let's let V be an element of the null space, and let W be an element of the range. All right, so first of all, to finish off the proof that the null space is a subspace of V, we need to show that if V is in the null space, that CV is in the null space. So in order to show that that is true, we want to see where T sends it. And so T is linear, so this is equal to C T of V. Well, T of V is the 0 vector, so this is C times the 0 vector in W, which is, of course, the 0 vector. And since T sends CV to the 0 vector, we know that CV is in the null space. And that really concludes that the null space is a subspace. We know that the range is a subgroup. All we need to do is show that, here I'm going to write down what we have to show. We have to show that, well, we know that W is in the range. We have to show that CW is in the range. So to show it's in the range, we have to show that CW is the image of some vector in V. Well, we know that W is. So let's see, W is in the range of T, implies that there exists an X in V such that T of X is equal to W. Well, let's see what T of CX is. T of C, that field element, CX, is equal to, T is linear, so it's C times T of X. And that is CW. So this means that there is an element in V that gets mapped to CW. This implies that CW then is in the range of T. So we have proven that the null space and the range are both subspaces of V and W respectively. 2 is a very important theorem. If T is a linear transformation from V to W, and beta is a basis for V, then the range of T is spanned by the images of those vectors in beta. This gives us a great way to find out what the range of a transformation is. And you'll see that in the next 3 problems. So really star this. It's not a hard proof, and it's very important for solving problems in this section. Okay, well, let's prove it. We want to show that these 2 sets are equal. So first, we'll just mention clearly the span of beta is a subset of the range of T. And now we want to show that the range of T is a subset of the span of beta. So let's let W, a vector W, be in the range. So we want to show that W is a linear combination of these vectors. Well, if W is in the range of T, then there is an X, a vector X, in V such that T of X is equal to the vector W. And beta, X is in V, beta is a basis for V. So we know that X, being a vector in V, is a linear combination of the vectors in beta. So let's say A1 V1 plus A2 V2 plus A sub n V sub n. Since beta is a basis, and therefore T of X, which is our W, is equal to T of, well, A1 V1 plus A sub n V sub n. And since T is linear, that is A1 times T of V1 plus A2 T of V2 plus plus A sub n T of V sub n. And that's exactly what we wanted to show, that W is a linear combination of the images of the vectors in beta. And it is, so we say then that W is in the span of this set up here, T of V1, comma, through T of V sub n. and therefore the two sets are equal. The range of T is equal to the span of that set. Let's go like that. Oh, one more thing before we start some problems is two new words. If the null space and the range are finite dimensional, which all of ours will be, then the dimension of the null space is called the nullity of T, and the dimension of the range is called the rank of T. So keep those definitions in mind. So now we'll do 3 examples. In each case, find the basis for the range of T and the null space of T. And then answer the question, what is the nullity and the rank of T? So our first example, T is the linear transformation mapping R3 to R2 by T of an ordered triple A1, A2, A3 is equal to an ordered pair A1 minus A2 to A3. So we'll find the range of T first. We know that the set containing, now let's just take the standard basis for R3. The range will be generated by T of 1, 0, 0, T of 0, 1, 0, the standard basis vectors of R3, and T of the ordered triple 0, 0, 1. This generates the range of T. So all you have to do is see what the linear transformation does to the basis vectors of V. So the linear transformation of these basis vectors is, well, we'll just look at the first one here. The first coordinate will be A1 minus A2. So that's 1 minus 0 is 1, and 2A3 is 2 times 0 is 0. So you just follow the instructions up here for the linear transformation T and find the image of the 3 basis vectors. Now, these are multiples of one another, so we could take one out. Those are linearly dependent. So we know that the set, well, let's just take 1, 0 and 0, 2. Those vectors generate the range. And so the rank is equal to 2, the dimension of the range. Okay, now let's find the nullity, the null space. The null space of T will be the set of all ordered triples A1, A2, A3 that are sent to 0, 0. So in other words, A1 minus A2 will be 0, A1 equals A2, and 2A3 will be 0, so A3 is equal to 0. And you can see that this would be generated by one vector, and it would have, well, we could put 1, 1, and then 0. That is a basis for the null space in V. If you multiply that by any constant, you get A1 equals A2 and A3 equals 0. So the nullity, the dimension of the null space, is 1. The nullity is 1, the rank is 2, and we know actually a basis actually for each of the 2 subspaces. This linear transformation takes R2 to R3, and this tells us what it does. I should have put other parentheses in there. T of an ordered pair in R2 gives us an ordered triple, where the first coordinate is A1 plus A2, the second coordinate is 0, and the third is 2A1 minus A2. So we know that the range, from the theorem that we just proved, the range of T will be spanned by the images of the basis vectors for R2. And I chose, of course, the standard basis vectors, 1, 0, and 0, 1. So let's see. It will be the span, then, of T of 1, 0 is the ordered triple, where I add the two, I get 1, 0 is the second coordinate, and 2A1 minus 0 is 2. The other vector, T of 0, 1, will have first coordinate 1, second coordinate 0, and 2A1 minus A2 will be negative 1. So we can see then that the rank, the dimension of the null of the range, is 2. These vectors are not linear, they are linearly independent, so they form a basis, and the rank is 2. Now let's look at the null space. The null space will be equal to the set of all ordered pairs A1, A2 in the domain R2, such that A1 plus A2 is equal to 0. The second coordinate is 0. The third coordinate, well, we have to have 2A1 minus A2 equal to 0 also. So if you take these two equations and solve them, you quickly find A1 is equal to A2 is equal to 0. So this is the set containing just the 0 vector. So we have the trivial null space, and we know that the rank of the set containing just the 0 vector, the rank is 0, the dimension is 0. Oh, excuse me, that's not rank. Nullity. The nullity is equal to 0. Our last example is a linear transformation from the vector space of polynomials of degree less than or equal to 2 to the 2 by 2 matrices with real coefficients. So again, we want to find out what the linear transformation does to the basis vectors, and that will tell us what set spans the range. So let's do that. Let's see. If our function is f of x equals 1, a constant, then f of 1 equals f of 2 equals 1, so we have 0, and these two are 0, and f of 0 is equal to 1. If our function is f of x equals x, then our f of 1 will be 1, and f of 2 is 2, so we get minus 1, and in the lower right-hand corner, f of 0 is equal to 0. So we get that 2 by 2 matrix, and if our function is f of x equals x squared, then the upper left entry will be 1 squared minus 2 squared, negative 3, 0, 0, and f of 0 would be 0 squared, or 0. Okay, well, we see that this vector is a multiple of that vector. So those two vectors are, oh, by the way, I should have had span here, the span of that set. But these two vectors are linearly dependent, so we can say that the range of T is the span of the set containing two matrices, 0, 0, 0, 1, and the matrix minus 1, 0, 0, 0. I could have just put 1, 0, 0, 0, 2. Wouldn't make any difference. So we have then a basis for the range of T. It has two matrices, so we say that the rank of T is equal to 2, the dimension of the range. All right, so now we want to find the null space. So the null space of T is equal to the set of all polynomials f in P2 of R, such that f of 1 is equal to f of 2. We have to get the 0 vector. So we want this to be 0 and this to be 0. So f of 1 equals f of 2, and f of 0 is equal to 0. So we'll have to think a little about this and to see what the polynomials in the null space look like. An arbitrary polynomial in P2 is equal to ax squared plus bx plus c. We want f of 0 to be equal to 0. So we know f of 0 equals 0 implies that c must be 0. So our function looks like ax squared plus bx. But f of 1 has to be f of 2. So f of 1 is equal to a plus b, and f of 2 would be 4a plus 2b. So solving for b, we get b is equal to negative 3a. So if our function is in the null space, it has to look like this. F of x is equal to ax squared minus 3ax. In other words, it's a multiple of the polynomial x squared minus 3x. So this gives us a basis for the null space. N of t is the span of this vector in P2, just the polynomial x squared minus 3x. So we see then that the nullity, the dimension of the null space is 1. The rank was 2, the nullity 1.